Hi everybody, hope you're having a wonderful day. Today we're going to start chapter 5, which is Thermochemistry. So as usual, we have the essential knowledge and the learning objectives for the whole chapter, and no exclusion statements in this one. So we'll start the chapter with the definition of energy, since this chapter talks about energy, specifically heat energy and chemical reactions. So energy is the capacity to do work or produce heat. That's something that we've probably learned about since middle school. Capacity to do work or produce heat. And work, which gets the symbol W, is the force acting over a distance. And you probably talked about this in physical science, or if you've taken physics. So if I wanted to calculate work, it's going to be force times distance. And you do not need to use this equation in chemistry, but it is useful just to understand what work means. So let's say that I push a cart, for example, from the beginning of the room, from the front of the room to the back of the room. I have done work. I've moved the cart with a certain force over distance. So if I wanted to calculate my work, I would figure out how much force I exerted over the distance that I've exerted and multiply them together. But let's say I keep pushing on a wall, and I keep pushing and pushing and pushing as hard as I can. I sweat. I'm so tired. I feel like I've worked a lot, but I haven't really done any work because there's no distance. My wall did not move. So it has to be a force over a certain distance. Heat, which is something that we're going to talk about a lot more in chemistry, is the transfer of energy between two objects due to a difference in temperature. So let's write that down. The transfer of energy between two objects due to a difference in temperature. And it always goes from hot to cold, never the other way around. So let's say I hold a hot cup of coffee in my hand. The coffee will transfer heat from its molecules to the molecules in my hand, because the average kinetic energy of the coffee particles is higher, which means it's hotter than the average kinetic energy of the molecules in my hand. Remember that the average kinetic energy is related to the temperature, so the hotter an object is, that means its molecules have a higher average kinetic energy. So if I hold a cup of coffee in my hand, the energy is going to transfer from the coffee to my hand. Let's say I hold a piece of ice in my hand. My hand is the same temperature, but the piece of ice, of course, is colder. So now my hand will transfer energy from my hand to the piece of ice. So it's always going from hot to cold. Let's say I hold somebody else's hand, and we're both at the exact same temperature. Well, then there's not going to be any net transfer of energy. Now, notice I said net. So if we are at the same temperature, there will be transfer back and forth. Even, when one thing is hot and the other one is cold, there is transfer back and forth. It's just that the hot is transferring more than the cold. So it's going from hot to cold. So if I hold something in my hand that's the same temperature, we are going to transfer energy to each other, but there's no net. So whatever I transfer to that person's hand is going to be the same as the energy that's transferred from that person's hand back to my hand. So no net. Sorry about that. I was holding the iPad tilted a little bit, so the screen went sideways. Anyway, first law of thermodynamics, you've all studied it from a long time ago, which says that the energy of the universe is conserved. Let's write that down. or is constant. So remember that we have a system, and then we have the surroundings. And chemists think of the whole universe, the whole entire universe, as my system, which is what I'm studying. It could be a chemical reaction in a flask, for example. So that's my system. And then the surroundings, which includes the flask and the air outside and the room and the whole world. And so the universe is made of the system and the surroundings. And of course, we can have energy transferring from the system to the surroundings or from the surroundings to the system. But together, the system plus the surroundings, so the whole universe's energy is constant. And we said that the energy is capacity to do work or produce heat. And so the change in internal energy is internal energy, which just means energy, is equal to heat plus work. So the internal energy can be produced by the flow of heat or work or both. And again, we're going to focus more on heat as opposed to work. Work is more of a physics concept. So objects can possess energy in two ways, kinetic and potential. So kinetic energy, remember, is, we typically use Ke for it. I've also seen it as E sub K. They both mean kinetic energy. So it is the energy of motion. And if you remember from physical science, or if you've taken physics, kinetic energy is equal to half mv squared. Again, you probably will not be using this equation in this class, but it is helpful to kind of look at it to understand what it means. So kinetic energy is related to the mass of the object, that's m, and then v squared, that's the velocity squared, so that's the speed of the object. And so the faster the particles are moving, the higher the kinetic energy, and the hotter the object. Potential energy is then the energy due to position. So let's write that down. And you can write as PE or E sub P. So it is the energy of position or composition. Now, some people think of this as stored energy. The problem with saying that it's stored energy is that it leads to a little bit of a misconception. I think you get this misconception initially in biology class, which tells you, well, let's say I have some fuel like gasoline or something like that, and I burn it, and I break the bonds, and the energy is released. That is a misconception. That is not true. Energy is needed, it's required to break bonds. So it's not that the energy is stored in bonds. The energy is due to the position of the particles. So if particles, for example, are really attracted to each other, if you put them close to each other, then they would have low potential energy. If you take those particles and you move them apart, like, if you have a longer bond or something like that, or a bigger internuclear distance between the atoms, then that would have a higher potential energy. And so when you break that bond, you still require energy to break it. Energy is not released when you break a bond. It's the other way around. So just be careful when you think of stored energy. So it has to do with the position of the particles. Typically, the closer the particles are, the lower the potential energy. The farther particles are, the higher the potential energy. It's the same idea as you are attracted to Earth. And so because you're attracted to Earth, the closer you are to Earth, if you are laying flat on the ground, then you have the lowest potential energy possible. Whereas if you stand up, then you have a little bit of higher potential energy. If you climb on a ladder or climb on a mountain, then you have a high potential energy because you are going far away from whatever's attracting you, which in this case is the Earth. And so when the particles are attracted to each other, the farther they are from that attraction, the higher the potential energy needed to keep them in that position. As we said before, heat is always transferred from hot to cold. So that means from high kinetic energy to low kinetic energy. So the faster particles, when they touch the slower particles, they make the slower particles go faster, and the fast particles, they get a little bit slower. So when the two systems are at different temperatures, meaning that they have different kinetic energies, when they come in contact with one another, the energy is transferred from the hotter to the cooler one until the temperatures are equal. At that point, the average kinetic energy of the particles in each of the systems becomes the same, and usually it's an intermediate temperature between, the hot and the cold temperatures. Let's talk about energy units. And so we use the SI units, which are joules. And so joules get capital K as their symbol. Now a joule is very small. Joule is how much energy you need for like a heartbeat. If you were to light a match, just a single small match, that's over 1,000 joules of heat that's released from that match. And so it's a very small amount of energy. And so we typically use kilojoules. Similarly, you can use calories, although we don't use it as much. It's more of an English system. And you can use the calories that start with a little c or the calories that start with a big C. So in science, if we use calories, it's usually the lowercase c. And let's define that. A calorie with a lowercase c is the energy needed to raise the temperature of 1 gram of water by 1 degree Celsius, or 1 Kelvin, either one, because a change in a Celsius is the same as a change in a Kelvin. So if I have a gram of water, which is a milliliter, which is a very small amount, and let's say right now I'm at 25 Celsius, that's room temperature, I want to raise it to 26 Celsius, that's how much energy is needed to do that. It's a calorie. So 1 little calorie is equal to 4.186 joules. You can use 4.186 or 4.184 joules, either one. And so a calorie is it's a little bit bigger than a joule. It's about 4 joules. So a joule is very, very small. Now, if you look at, if you look at your snacks or foods that you buy, and they have the nutritional values on the back, the calories there are always listed as big calories. So 1 big calorie is equal to 1,000 little calories, or you can say it's a kilocalorie. So if you think about it, the average person needs about 2,000 calories a day. Those are big calories, which means you need about 2 million little calories a day, which is more than 8 million joules a day. So again, a joule is a very, very small amount of energy. So our focus for this chapter will be about heat. And, if it's a physical change, or if, we're heating up a cup of coffee or something like that, we usually use the word heat. But in a chemical reaction, we typically use the word enthalpy. So enthalpy is the same thing as heat. It's just specific to a chemical reaction. So let's first define enthalpy here. So it is the heat transferred in a chemical reaction. The symbol for enthalpy is delta H. The symbol for heat is lowercase q. And again, heat and enthalpy are kind of the same thing. It's just typically we use enthalpy for chemical reactions, whereas heat is just, for other processes that involve heat transfer. If we are talking about a chemical reaction, like I said, we use enthalpy, delta H of the reaction. And so it's the change of the heat content as you go from the reactants to the products. And so whenever you're talking about a change of anything, it's always final minus initial. So it would be the heat content or the energy of final minus initial. So products would be our final minus the heat content of the reactants. So we have two types of thermal reactions. We have exothermic reactions and endothermic reactions. So remember that exo means out, thermic means heat, and we're always referring to our system. So when we say that it's exothermic, we are saying that the heat is going out of our system. Heat going out of our system. Where is it going to go? It's going to go to the surroundings. So let's write that down. System releases energy to surroundings. Okay. So if I have my reactants having a certain amount of potential energy, and so if I wanted to draw an energy diagram, this is potential energy. We can use it labeled as H, or we can use it as potential energy, either one. Our x-axis could be time or reaction progress. And so at the beginning you start with your reactants. So your reactants are somewhere here. If you know what your reactants are, it's preferable to write that down. So for example, if my reaction is between magnesium and oxygen, then I write Mg plus O2 where the reactants are. Now if it's an exothermic reaction and the system is releasing energy, that means that if I'm right here having a certain amount of energy, those reactants release or lose energy to the surroundings to get to the products. And so if they're right here and they're releasing some energy, that means the products are going to be at a lower energy. So let's say my products are right here. And again, if you know what your products are, like let's say my example of magnesium and oxygen, then in the products I would write MgO, for example, as opposed to the word products. Now we all know, we remember from last year, that it doesn't go directly downhill like that. It goes up in a little hill and then it goes down. The difference between the products and the reactants, that's my delta H. And in this case, remember that delta H will be negative if it's exothermic because my delta H of the reactions products minus reactants. So I have a smaller number minus a bigger number. So a small number minus a big number, that's going to give me a negative value. So my delta H for an exothermic reaction is negative. That's one of the ways that you know that it's an exothermic reaction. That top of the hill there, that's your transition state. So the transition state is a state in between the reactants and the products. So in order for this reaction to happen, the particles in the reactants have to collide together. So they keep colliding and they fall back down. They keep colliding and fall back down until they collide with enough energy to reach that transition state. That transition state is a state where it's the substance kind of looks a little bit like the reactants, a little bit like the products. So your reactant bonds are starting to break and your product bonds are starting to form. Sometimes we call that the activated complex because it's kind of complicated and it has a pretty high energy. And remember that anything with a high energy means that it's not very stable. So most transition states don't live for very long. It depends on what they are. Some exist for a few minutes, some exist for a few hours, some exist for femtoseconds, so it depends. But it's not very stable. Most of them, decay or not decay, but turn into products within microseconds maybe. So this transition state has the highest amount of energy, meaning that it's the least stable out of them. Now, in order to get to that transition state, the reactants need a little bit of a push, and so we call that push the activation energy. And so the activation energy is from where the reactants are to that top of the hill. This is your activation energy. So that's how much energy I need to give it. It's a little push to get it to react. Now, let's look at our diagram and the difference between the reactants and the products. We said because the reactants are releasing energy, this amount of energy is being released to get to the products. The products have a lower amount of energy than the reactants. So let's write that down. Products have lower potential energy than the reactants. Now notice that the difference between the reactants and the products, that's potential energy that we're talking about, that they lose or gain or whatever. So that has nothing to do with temperature, that has to do with the position. So this position of particles is preferable. It's easier for those atoms to exist in this position compared to this position, so they require less energy as products compared to reactants. Now, when this energy is released, it is released to the surroundings. Now, the surroundings then take that energy in the form of heat. So the particles in the surroundings get faster and faster because they get hotter because you're adding more energy. And so because the surroundings are getting hotter, my system is also getting hotter just because the surroundings are touching my system. So in an exothermic reaction, everything gets hot. My system itself doesn't really change in kinetic, it changes more in potential energy. The position of the particles have rearranged, so my potential energy is different. But because it releases the energy to the surroundings get hotter, and so everything gets hotter. So that's one way to know that it's an exothermic reaction, is if it feels warm. And an example of an exothermic reaction is combustion reactions. All combustion reactions release heat, so all combustion reactions are exothermic. Remember that if you see fire, or if you see a flame, it's an exothermic reaction. All right, let's move on to endothermic reactions. So just like I'm going to label this as potential energy, and this is as time or reaction progress. So endo means in, thermic means heat. So the heat is going in, and again, we're always talking about our system, so the heat is going into our system. Where is it coming from? It's coming from the surroundings. So the system is taking in the energy, or absorbs energy from surroundings. So let's say your reactants are at a certain amount of energy here. And these reactants are going to absorb energy in order to become products. So if I'm absorbing energy to get to the products, that means that the products must be at higher energy. So products have higher potential energy than the reactants. Again, it doesn't go directly. You have like a little hump before it goes down. The difference between the products and the reactants is my delta H, and in this case, my delta H is going to be positive. That's because delta H is always products minus reactants. Higher number minus smaller number is going to be a positive number. My activated complex, or my transition state, is still at the top of the hill. It's the highest amount of energy, so it's the least stable. And from my reactants down here all the way to the transition state, that's my activation energy. My reactants and products differ in potential energy, the position of the particles. So this position of particles is less favorable. It's requiring more energy to hold the particles at this position compared to this position. So it is potential energy that differs between my molecules in my system. Now, as the system absorbs energy from the surroundings, it is absorbing that energy from the surroundings. The surroundings are losing heat energy. So even though the surroundings are losing heat energy, it's going into my system as potential energy, adding potential energy to my particles. But because the system is losing heat energy, the surroundings are getting colder. And so as the surroundings get colder, because they are touching my system, everything feels colder. So if I were to measure the initial temperature and then the final temperature, my final temperature will be lower. It'll be colder than my initial temperature. And here is a summary of what we just talked about. So exothermic reactions, that the heat flows out of the system into the surroundings. Everything gets hotter. We write the reactants on one side, the products on the other side, and since the system is releasing the energy, it's losing the energy, it's producing the energy, so we think of the heat as a product. And remember, the delta H in this case is negative. For an endothermic process, the heat is going into my system from the surroundings. And so the system is absorbing energy, so we think of energy here as a reactant. So we're adding in energy to my reactants in order to get the products. And so my delta H in this case is going to be positive. So in general, when we think of heat released, we say it's negative. When we say heat is absorbed, we say it's positive. So there's not really a negative energy. There's no such thing as negative energy. It just means which direction it's going. So when we see negative next to like delta H or negative next to joules or kilojoules, that tells us that it's being released, that it's an exothermic process. When we see a positive, that means it's going into my system, so it's an endothermic process. So let's start actually calculating how much heat is released or absorbed through different processes. The simplest way to calculate the heat or the enthalpy is using Q equals mc delta T. We call that the MCAD equation. And maybe when I come back we can play the mc delta T song. It's one of my favorites. So Q stands for heat. And the units for the heat is going to be joules in this case. M is your mass of your object, which is in grams. C is specific heat capacity, which is in joules per gram Celsius or joules per gram Kelvin. We'll talk about what specific heat means in a second. And then delta T is change in temperature. So it's not just temperature, but change in temperature. It's T final minus T initial. And so this should be in degrees Celsius or in Kelvin. It's going to be the same value whether it's degrees Celsius or Kelvin. Same thing with C. It's going to be the same value also if it's in joules per gram Celsius or joules per gram Kelvin. Now, we use Q equals mc delta T. Typically, if you are looking at one substance and it's at the same phase. So I take some water, for example, at room temperature, let's say 25 Celsius, and I warm it up to, 95 Celsius so I can make a cup of coffee. So as long as it's staying as liquid water, so it's in the same phase, and I'm only discussing one type of substance, then I can use Q equals MC delta T. Now let's talk about that C a little bit more, specific heat capacity. So specific heat capacity is, let's write the definition for it. It is the amount of heat needed required to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin, again, same thing. Now this definition should sound very, very familiar to you, right? It sounds just like the definition of a calorie, except there's one word that's different. In a calorie, it's raising 1 gram of water by 1 degree Celsius, as opposed to here, raising 1 gram of any substance. So a calorie is actually the specific heat of water, specific heat capacity of water. So let's think about this. It's how much energy I need to raise 1 gram of my substance by 1 degree Celsius. So if I have a low heat capacity, what does that mean? Like, if you look at your metals, for example, you'll find some metals with like 0.1 joules per gram Celsius, or 0.3 or 0.9, something like that. They're relatively smaller numbers. Compared to water, for example, it's 4.186 joules per gram Celsius. So what does that mean? Well, if you have a low heat capacity, that means you only need a little bit of energy to raise your temperature for 1 gram of your substance. So a little bit of energy will raise its temperature, which makes sense. Metals, if you think about it, like let's say if you go out and it's a really hot day and there's a metal bench, you don't want to sit on that because we know that metals have a low heat capacity, meaning that it requires just a little bit of energy to raise its temperature. So if the sun hits that metal, it's going to be super hot because it's very easy to raise its temperature. Same thing going the other way to cool it down. It requires very little energy to be released in order to cool 1 gram of my substance by 1 Celsius. So when it's a snowy, cold day, you don't want to sit on that metal bench either because it's going to be very, very cold. Whereas water, it takes a lot of energy to change, relatively, to change its temperature. So that's why oceans moderate the climate on Earth, because of the high specific capacity of water. It takes so much energy to raise the temperature of the water in the oceans, and we have lots of water bodies on Earth, and so the climate on Earth is moderated because of how much water we have on Earth. Okay, let's look at this problem here. It says, let's say I have 10 grams of aluminum and 10 grams of copper, both at the same initial temperature, so same mass and same temperature. Which substance needs to absorb more energy in order to raise its temperature by 10 Celsius? So in order to do that, we got to look at the specific heat capacities of aluminum and copper. So if you look up the values for the specific heat capacities for aluminum and for copper, I read them down here. They're in your tables there. So aluminum is 0.902 joules per gram Celsius. Copper is 0.385 joules per gram Celsius. So we need about 0.4 joules for every gram to raise it by 1 Celsius. For aluminum, we need 0.9 joules for every gram to raise it by 1 degree Celsius. So which one would absorb more energy to raise its temperature by the same amount? Well, you would need to absorb more energy by the aluminum. So for 10 grams to raise it 10 Celsius, it would be 90 joules for the aluminum and only 38.5 joules for the copper. But you don't even need to think about numbers as long as you're starting with the same amount, same mass, and same initial temperature, and the same change in temperature. Then you just look by the specific heat capacity. So this one needs more. So the answer is the aluminum. Okay, let's look at the next question. It says I have 10 grams of water, sorry, I wrote over it, and 10 grams of mercury, both at 25 Celsius. So again, same amount, but and same initial temperature. If both of them absorb the same amount of energy, they're both absorbing 20 joules of energy. Which substance would have a higher, that should say, final temperature? So let's look up the specific heat capacities for water and for mercury. So I looked them up. Water is 4.18 joules per gram Celsius. Mercury is 0.45 joules per gram Celsius. To be honest with you, actually, we didn't really need to look them up because you know mercury is a metal. It's going to be lower than water. But anyway, water's about almost 10 times as much as mercury. So what does that mean? So it takes 4 joules of energy to raise 1 gram of water by 1 Celsius. It takes only 0.4 joules of energy to raise 1 gram of mercury by 1 degree Celsius. So if both of them are taking in the same amount of energy, they're taking 20 joules, which one would its temperature be more different, be higher temperature? Well, the answer would be, in this case, mercury, because mercury takes only a little bit of energy to change its temperature, whereas water takes a lot of energy to change its temperature. So if you're giving them the same amount of energy, mercury is going to change drastically compared to water. Specific heat capacity questions have been popular on the AP exam, so just make sure that you understand what specific heat capacity means and you can compare between different substances like that. All right, let's do a couple of questions using Q equals MC delta T. So this one says, how many joules of energy must be lost for a cup of water to drop its temperature from 60 Celsius to 37 Celsius? It says the volume of the water in the cup is 250 milliliters. So it looks to me like we're only talking about one substance, which is water, and it's not changing its phase. It's remaining as a liquid. And so one substance, same phase. Looks like I can use Q equals MC delta T for this one. So let's write that down, Q equals MC delta T. Let's see, what are we solving for? Well, it says how many joules of energy. So I'm solving for the amount of energy, which is my Q. My mass is not given, but I am given that it's 25 milliliters. And I know that the density of water is 1 gram per milliliter. So I can say, well, this is 1 gram per 1 milliliter, and so it's 250 grams. So I'll plug that in. C for water is 4.184, and again, you can use 4.184, 4.186, either one is fine. I think even in one of your tables, it just says 4.18, and that's it. Just joules per gram Celsius. All right, and then delta T, it says it goes from 60 to 37. So delta T, I'll write it down here, is T final minus T initial. So you can do it on the side and plug it in, or you can do it all at once. 37 Celsius is my final minus 60.0 Celsius is my initial. Plug that into your calculator, you get Q is equal to negative 24,100 joules. And that's my answer. Now, what does that negative mean? It means that the energy is released or lost, which makes sense because I'm losing energy in order to cool my my cup of water. So you can write it as negative like that, or sometimes it gets a little confusing because the question is asking, well, how much is lost? So technically could use the positive value and because the question's saying lost, and so it can get confusing. So my preference is, as opposed to putting the negative there, I would write 24,100 joules lost, as opposed to putting the negative there. You don't want to put the negative and say lost. You want to either put the negative or say lost or released. So my preference would be, so to avoid any confusion, you write the word released or lost. All right, let's try one more. It says if the same amount of heat was used to heat aluminum metal from 37 Celsius to a higher temperature. What maximum temperature would be reached? Assume the mass of the aluminum was the same as the water. So this one relates to the one that we just did. So the water lost some heat. It cooled down by releasing some heat. That heat was absorbed by the aluminum. It was used to heat up a piece of aluminum. We want to know, well, how much higher is the temperature of the aluminum? So let's think about this. So we're saying the heat lost by the water is equal to the heat absorbed by the aluminum, or gained by the aluminum. So that means that Q of the water is equal to negative Q of the aluminum. Now the negative there tells you that it's the opposite sign, which means if the water is releasing, then the aluminum is absorbing. Now if that bothers you, you don't have to write that down. So water's energy was negative 24,100 joules because it was releasing. So if you put a negative in front of that, then it's going to be positive 24,100 joules. That's my Q of aluminum. This is Q of aluminum. So then what I can say is, well, Q equals MC delta T for my aluminum. My Q of aluminum is positive 24,100 joules. My mass of aluminum, it says it's the same mass as water, so 250 grams. C for aluminum, we look up. It's 0.902 joules per gram Celsius. And we put delta T. It's easier math if you put delta T there. If you want to put T final minus 37 and solve for what T final is, that's fine. It's just a little bit more algebra. So it's a little bit easier to do it that way. When you do this, you get delta T is equal to 107 Celsius. So then I'm going to say delta T is T final minus T initial. So 107 Celsius is equal to T final minus 37 Celsius. So T final is equal to 144 Celsius. Now, one last thing I want you to look at. The heat that was released by the water was absorbed by the aluminum. Let's look at the water. The water went from 37 Celsius to 60 Celsius. So it went up by about 23 degrees. Okay? That same amount of heat changed the aluminum from 37 Celsius to 144 Celsius. That's more than 100 degrees. Now they were the same amount, same 250 grams. So what's the main difference is? It's the specific heat capacity. The specific heat capacity for water is much, much higher than the specific heat capacity for aluminum. All right, that's it for today. Tomorrow we're going to talk about different ways to calculate delta H or Q. Have a wonderful rest of your day.